All right, today we are going to crack a cosmic code. We're talking about a really strange message sent from an even stranger source. So, picture this. Way out there, 2,100 light-years away, a dead star is beaming a signal straight at Earth. But the thing is, the signal we get is all warped. It's scrambled, like it's been passed through some kind of cosmic funhouse mirror. So our mission today is to figure out what's causing all that distortion, and what it can tell us about the hidden fabric of our own galaxy.
So first, let's meet the source of this bizarre message. Turns out, it's a dead star with a very peculiar secret. Okay, meet Pulsar B0834+06. Now, I know that's a mouthful, but it's also got a much cooler nickname, LGM-2, which stands for Little Green Men, 2. Seriously, that name is a throwback to when these things were first discovered by Jocelyn Bell. The pulses were so perfectly regular that for a hot second, people half-jokingly wondered if they were signals from aliens. Now we know it's a pulsar, a spinning dead star that acts like a cosmic lighthouse. And this one sweeps its beam past Earth with unbelievable precision every 1.27 seconds, like clockwork.
A lighthouse beam is great, but only if you can see it clearly, right? Well, LGM-2's signal isn't clear at all. It twinkles, it shimmers, it changes, and that tells us something huge. The vast emptiness of space isn't actually empty. Something is out there, getting in the way of the light on its 2,100-year trip to get to us. Let's find out what it is. To solve this mystery, scientists basically had to become cosmic detectives. And their very first piece of evidence? The signal itself. And this is what the raw data looks like. It's called a dynamic spectrum. You can kind of think of it like a chart a music producer would use, with radio frequencies on one axis and time on the other. All those bright spots are where the pulsar signal is coming in strong, but just looking at it, it seems like a total mess, just random static, a chaotic jumble of bright and dark specks.
For the longest time, everyone just chalked this up to noise, a random pattern caused by turbulence in deep space. But the question is it really random? Or is there some kind of hidden message, a hidden order, buried inside all that chaos?
Turns out it all comes down to how you look at the data. Scientists took this messy-looking chart and ran it through a really powerful mathematical tool. It's called a Fourier transform. It's basically a technique that's designed to find any hidden rhythms or repeating patterns in a signal. And it converted this chart into something brand new called a secondary spectrum.
And what they found was an absolute breakthrough. The random static, it just transformed. Out of all that noise popped these two incredibly sharp, perfectly formed parabolic arcs. This was the smoking gun. You just don't get clean, geometric shapes from a random process. This pattern proved the pulsar's light isn't just being scattered randomly. No, something in space is splitting and bending the light along specific multiple paths. And when all those different paths arrive at our telescopes, they interfere with each other, creating this beautiful, organized pattern.
And these arcs aren't just pretty, they are incredibly useful. The exact curve of that parabola is directly tied to the geometry of the whole situation. By measuring that curve, scientists could calculate precisely how far away that cosmic fog is. And for LGM-2, this scattering screen is about a third of the way between the pulsar and us, around 700 light-years from Earth. We're actually starting to map the invisible.
This whole discovery led to an even bigger leap in thinking. Scientists started to wonder, what if this distorted signal wasn't just a clue about the cosmic fog? What if it was a complete picture of it?
And this is where the idea of interstellar holography comes in. You know a regular hologram, right? Like the little shiny thing on your credit card? It stores a full 3D image on a flat 2D surface using an interference pattern. Well, scientists realize the pulsar's dynamic spectrum is exactly that. It's an inline hologram of the stuff between the stars. The pulsar is the clean light source, the gas cloud is the object, and together they create an interference pattern that holds all the information we need to reconstruct an image of the cloud itself.
And the improvement this brought was just staggering. I mean, earlier attempts to make an image were crude. They could only see the very brightest parts of the signal, maybe 16 decibels worth, which left huge errors. But this new holographic method, it can model the entire 63 decibel range of the signal. We're talking about the difference between a blurry, incomplete sketch and a perfect high-res photo. It's night and day.
So the technique is obviously incredibly powerful. But what did it actually show us? What does this invisible cosmic fog really look like?
This quote from the research paper really says it all.
After they applied their holographic model, the tiny little bit of signal that was left over, the difference between their model and the real data, was basically indistinguishable from pure random noise. That's a scientific way of saying we nailed it. Their reconstruction was essentially perfect.
They had done it. They successfully reversed all that distortion and created a detailed map of the interstellar gas cloud that was scrambling the signal from LGM-2. They were literally seeing the invisible.
And the picture it painted was absolutely fascinating. This cosmic fog isn't some smooth, uniform mist at all. It's incredibly patchy and thin, what scientists call anisotropic. It's filled with these distinct, dense, localized blobs of plasma. And it's these little structures that act like tiny lenses, splitting the pulsar's light and creating those amazing parabolic arcs in the data.
Okay, so we can map a gas cloud 700 light-years away. That's really cool, no doubt. But why does any of this matter for science back here on Earth?
Let me just throw a number at you, 15.2. That number, 15.2, is the average delay in microseconds that this patchy gas cloud adds to LGM-2's signal. See, because the light is taking a bunch of different paths with different lengths, the pulse gets smeared out over time. And this delay isn't constant. It fluctuates like crazy as the pulsar moves behind different parts of the cloud. One day, the delay might be 10 microseconds. The next, it could be 20. And this is where the stakes get incredibly high, because that unpredictable delay, it's a huge problem. Scientists use the ultra-precise timing of pulsars as these giant galactic-scale clocks. They use them to test Einstein's theory of relativity and to hunt for the faint ripples in spacetime called gravitational waves. An uncorrected, random delay of 15 microseconds is a massive error that can completely ruin these super-delicate experiments. But now, with interstellar holography, we can measure that delay precisely for every single pulse and correct for it. We've literally turned a source of noise into a powerful new tool.
So just think about where we started. A scrambled signal from a dead star nicknamed Little Green Men 2. And by decoding it, we not only solved the mystery of the distortion, but we also found a way to see the invisible structures between the stars. It just leaves you with this amazing thought. If one single pulsar can give us a high-res map of one tiny patch of the cosmos, what could a whole network of these cosmic lighthouses show us about the hidden architecture of our entire Milky Way galaxy?